Alright, in this last video in sections 12.1 and 12.2, we're going to discuss spheres in R3, and then we'll look at the last three questions, 9, 10, and 11, on the worksheet. Alright, so let's say we have a sphere S in R3, and its center is located at the point whose coordinates are H, K, and L, and the radius of the sphere is R. And let's let P be a point on the sphere, and I'll label its coordinates X, Y, and Z. Okay, well, point will be on the sphere provided the distance from that point to the center is equal to the radius of the sphere, right? That's really the defining characteristic of all points on a sphere, right? They're a fixed distance from the center, and that distance is what we call the radius of the sphere, okay? So applying our result from the last video about distances, right? The distance from P to C, right, is the square root of the sum of the squares, where in each of the squared terms, I'm just taking the difference in each of the respective coordinates. So x minus h quantity squared, y minus k quantity squared, and z minus l quantity squared. And that distance must equal the radius r. Okay, so squaring both sides, this gives us what we'll call the standard form equation of the sphere of radius r centered at the point C, whose coordinates are h, k, and l. So notice this looks just like a circle equation, okay? But now we have this extra term incorporating the z coordinates. Now, if the center of the sphere happens to be at the origin, right? So in other words, h, k, and l are all 0, this simplifies to the equation x squared plus y squared plus z squared is equal to r squared. All right, cool. So now, with all that in place, let's go ahead and check out question 9 on the worksheet. So it says, describe all points x, y, z that lie on the intersection of the sphere x squared plus y squared plus z squared is equal to 61, and the plane y equals 5. Okay, so first off, this equation x squared plus y squared plus z squared is equal to 61. Well, based on what we just saw, right, this describes the sphere of radius root 61 with center at the origin. Okay, so you see that here in blue. Now, y equals 5, as we saw in a previous video, right, this describes a plane, and more specifically, right, it is the xz plane shifted 5 units along the positive y-axis. Okay, so if I go ahead and put that plane in the picture, we want the intersection of the sphere and the plane. So what is that describing? Well, it's describing a circle. And how can I find, say, its radius? Well, go back to the equations of the sphere and the plane, right? So all points on the circle of intersection, right, have for their y-coordinate 5, right, because the circle lies in the plane, y equals 5. So if I put 5 in for y in the sphere equation and then rewrite, right, I get the equation x squared plus z squared is equal to 36. So this is the circle in the plane y equals 5 with radius 6, right, because there's a 36 there on the right side. And the center there will be at this point right here with coordinates 0, 5, 0. All right, great. So now moving on to question 10, it says, find the equation of the sphere with antipodal points P, whose coordinates are 2, 1, 3, and Q, whose coordinates are 0, 3, 5. Okay, so what does this word antipodal mean? Well, we say that 2 points, P and Q, are antipodal, provided the line through P and Q passes through the center of the sphere. Okay, so if I'm thinking of the sphere as, say, a globe, they're on opposite ends of the globe. Okay, so how can we go about finding the radius of the sphere? Well, as you see here in the diagram, one way to approach this would just be to find the distance from P to Q, or in other words, the magnitude of the vector from P to Q, and then I just want half of that distance, right? Because the distance from P to Q would be the diameter of the sphere, so the radius would be half. Okay, well, finding the vector PQ, as we've been doing, right, you just subtract coordinate-wise and then its magnitude. As you can see here, I'm computing as the root of negative 2 squared plus 2 squared plus 2 squared, and this all simplifies to the root of 3. Okay, so the radius of the sphere is the square root of 3. And then how about the center? Well, the center is the midpoint, right, of the points P and Q. So how can I find the coordinates of the midpoint of 2 points? Well, the idea there is just to average the x, y, and z coordinates of the 2 points. Okay, so the coordinates of the center C, I'm just going to take the average of the x coordinates of P and Q, so 2 plus 0 over 2, which is 1. That's the x coordinate of the center. For the y coordinate, we'll just average the y coordinates of P and Q, so 1 plus 3 over 2, and that's 2. And then lastly, for the z coordinate, 3 plus 5 over 2, and that's 4. Okay, so our sphere has a radius of root 3 and a center with coordinates of 1, 2, 4. So putting that all together, right, for our standard form of a sphere, we have x minus 1 quantity squared plus y minus 2 quantity squared plus z minus 4 quantity squared, and that's got to equal the square of the radius. So we need a 3 there on the right side. All right, great. And so then to finish, let's look at question 11. It says, write an inequality that describes the solid ball of radius 3 and center at the point negative 2, 0. Okay, well, first off, what's the equation of just the sphere of radius 3 with center at negative 2, 0? Well, that would be x plus 2 quantity squared plus y squared plus z minus 4 quantity squared, and that's going to equal the square of the radius, so that's going to give us a 9 on the right side. So that describes all points on the sphere. So then for the solid ball, I want all points on the sphere and all points inside the sphere. So, in other words, I want, right, everything on and inside the sphere. And so here I'm just going to replace this equal sign with a less than or equal to, okay? And that's going to do it. Thank you so much.